Well, here we've got our reaction with an equilibrium constant, a Kc. It's for concentrations, and immediately we say, okay, we're just going to deal with molar stuff. Don't have to worry about partial pressures. This is the formation of NOCl chloride, a pretty exotic compound. It's formed when you mix nitric acid and hydrochloric acid together to make aqua regia. Is involved in the dissolving of gold. Again, really exotic, very, very nasty. You don't want to be around this. The reaction is pretty complete if you make it from nitrogen monoxide with chlorine. They basically burn together. In fact, nitrogen monoxide and oxygen will burn together. But here we've got this reaction. It's an equilibrium. But when we see a number this large, 65,000, we know that we're going to get a lot of this product and not that much reactant left over at equilibrium. So let's see, they do the experiment and they give this in the right order where they've got a small amount of nitrogen monoxide and a also even smaller amount of chlorine, both of these reactants. It's important to differentiate and look at the quantities of the reactants. And also, rather than just starting with reactants, they have a bunch of product in there too. They've mixed them all together. In this case, a lot of them, 6.30. Now notice these are moles. These aren't concentration, and they're mixed in a 2-liter flask. So we're going to have one part of this problem where we find out the concentrations. And they want to find out what the reaction quotient is. In other words, what does this mixture look like in terms of an equilibrium expression? Well, we've got to figure out the equilibrium expression first, which is products over reactants. Now, one thing to look at first before I do any writing, I see all of these are gases. There's no solids involved in here. So we're good. We can use everything. If this had been a solid, we would have said, okay, we're not going to include that. That makes the problem simpler. But this one can't be simplified. So we'll have to have products. Here's our NOCl chloride. And we'll make that as a numerator. It's the products over the reactants raised to their coefficients. This isn't like the rate law expressions where we've got to figure out slow steps in reactions and rates and stuff. No, we just use the coefficients. This is nice and simple. So there's a squared involved, and here's a coefficient of 2, so we know that's going to be squared 2. Don't forget those coefficients. They're critical in the equilibrium expression. And then we just have 1 as our coefficient for chlorine, and now we've got our equilibrium expression. If these concentrations are calculated and raised these powers and divided, we should get 65,000 as our answer for this temperature. It's an amazing thing that these chemicals would move and shift around this way. And that's what we're going to see if that's happened. Is this correct? Do these concentrations that we have multiply out to make 65,000? We're checking it out. This is the Q, the test. So I'll put the numbers in. As I warned you, you've got to make sure that you get the concentrations. And I probably should have put a molar brackets here rather than parentheses. Please, I'm not going to redo this, but I think if I was going to redo this again, I would put brackets here to indicate molar concentration. But I was thinking about this in terms of mathematics, so I use the parentheses. So I'm going to take this 6.3 divided by 2 and then squared. And then I'm going to divide it by the reactants, the NO squared, again, with this concentration and this here too. Now this is a pretty involved calculation. Now if you'd set this up, you probably would have, on an FRQ, you probably would have gotten 1 point for the correct equation here, using the brackets to indicate molarity. I'm pretty sure they wouldn't deduct points for these parentheses rather than using the brackets because they figure you're doing the math. So let me do the math. I'll bring my calculator up, my trusty TI. Now you could do this the long way, but I see right here that this 2 squared and this 2 squared are going to cancel. So I won't have to worry about this divided by 2 in both of these expressions. So I'm going to make my math a little bit easier. I'm going to take this 6.3, and I don't have to divide by 2. In fact, let me just do a little, I'm going to pull out my line and say, okay, I'm going to cancel this and cancel this. Your algebra can help you. This is one of the reasons chemistry classes require an algebra component before you get there. So I'm going to divide this by 2. No, I'm not. I decided not to. Take that back. I'm going to delete. But I am going to square it. So I'll square it and get my answer. 39, that makes sense. 6 squared is about 36, so this is a little bit more than that. And I'm going to divide that by you could use parentheses, but I know the order of operations of my calculator, and it does the squared first before it divides. And I don't have to worry about the division by 2. That makes my calculation easier. And I'd expect to get a large number because I'm dividing a fraction squared into this. And then I'm going to divide again, in this case, by the 0.0082. You could have used the parentheses, but I'm going to use my algebra and realize the denominator of a denominator, it becomes a numerator, and I'm going to multiply this answer by 2. Again, you can do your own calculation to see if you get it right. I feel comfortable using my algebra, and I've used this calculator a lot. I've double checked. Now let's see what my answer is. Again, I expect a large answer, and indeed I get one. Let's see. 1, 2, 3. I get times 10 to the 7, 3.78 times 10 to the 7. And let's see if that's the correct answer. I'm going to grab my little tool and find out if I get 3.7 times 10 to the 7, 3.78. This is a big number. This is 38 million compared to the 65,000 I should have gotten. So this reaction isn't at equilibrium, because if it's at equilibrium, all these numbers would have multiplied out to make 65,000. Which would have been nice. I said, this is at equilibrium, everything is fine. We won't be seeing any changes. But no, this number is it's significantly larger than the 65,000. We've got too much of our numerator and too little of our denominator. We've got to make this number smaller. So the next question that comes up is, how will the rates of the forward and reverse reactions compare? There's a number of choices. We can have the forward reaction go to make more products. Here's our little alligator, where my Q is greater than my K. If they're equal, then our forward and reverse reactions will be the same. But if we have too much Q, note this is a greater sign, our alligator is going to go in this direction. Our reverse reaction will go. That's the mnemonic people use, but you should realize how it makes sense. That's important, knowing the logic behind this. And let's look at this. Now we've got this reaction going backwards, our mnemonic with the alligator greater than sign, which means that this stuff, the NOCl, concentration is going to decrease. It's going to go down. And if it goes down, that means this number has to become smaller. Our QC becomes smaller, and it will become smaller and smaller and smaller. At the same time, because this reaction is going backwards, it's making more chlorine. It's making more NO. In fact, the coefficients are, for every 1 NOCl, you're going to get a half a NOCl, you get a half a Cl, and you'll get 1 NO. So these two numbers are going to run down. We could do a minus 2x and a plus 2x and figure it out until finally all the concentrations are such that when we take the concentration of the NO squared and divide it by the concentration of the NOCl squared and divide it by the concentration of the NO squared and the Cl, we'll end up getting 65,000. So that's our equilibrium expression and problem. This could have been, my guess, is a pretty close to a 10-point FRQ. This could have been 10% of the AP exam. So this is a good exercise, and I hope you understand it in addition to knowing this mnemonic. Okay, signing off.